Alrighty. Well, this is where we left off last time. We really stopped with the idea of a D latch, right? Or the D flip-flop, actually. And remember that the D flip-flop was great in that whatever signal was coming in on the data line would get latched in, would get stored in that design every clock pulse. But the issue there was that, well, what if we don't want, like, usually what happens is we have a data bus, which is one giant signal, one giant collection of signals, one for each bit, that is the main thing that transfers information around the system. And like everything's hooked up to this bus. If data is being sent to somewhere, it's coming from the bus. If data is being sent from something to somewhere else, it's going to the bus. And the bus is what transfers it around. So there's all this data on the bus all the time, but we might not want the data from the bus to be put into the register. But the way the D flip-flop is designed is whatever data is there, every time there's a clock pulse, it gets latched in. We don't want that to happen. We want a little bit more control. So what we do is something like this. Now I'm actually not 100% clear on why this is the design, but this is a design for a register. What we're doing is, this is the D flip-flop, okay? But notice that its output is, okay, its output's its output. I'm ignoring Q naught because we don't really care right now. But you'll notice that its output is being fed back in to this, what is this called? Who remembers? A multiplexer. Select one of these signals to send there. So it's a multiplexer. It's a multiplexer with an enable bit. It can either be 0 or 1. When it's 0, disabled, really it's a select bit, right? But this, I'm thinking this is like an enable for this design here. When it's not enabled, the data that gets latched in will be itself. We just reload itself into there. When it's high, meaning we are enabling it, the data from the data line goes in to this and gets latched in. So either we restore what value's in there, or we overwrite whatever value's in there with whatever's coming from D. Cool? Now, why is it that we need this looping system here, right? Well, I'm sure we could come up with another design for this system, but you could say, well, either store the data that's on here, right? Or if I disable, like, why could I not do something along the lines of, here we go. Like imagine I have this D flip-flop, D clock Q, okay? Why do this whole looping thing and not just have like an AND gate, right? With like an enable signal, the D signal, and then whatever the clock is coming from. Why not do something like this, right? Why go through this whole rigmarole of looping whatever's in there back into the thing? If I can just set this to 0, we disable whatever that data bit is. But remember, why is this important? Because every time the clock pulse, it stores whatever's here. So if we disable the data bit, disabling it is setting it to 0. And every time that clock pulses, this would get set to 0. So we have no way to really disable the input. All we can do, because this latch is always going to read something. It must read something. A 0 or a 1. If we want it to store whatever's there, we actually just restore itself. Because the clock pulse, it's going to store whatever's there. If we disable the data, well, that's a 0, and then we store a 0. No good. We need that funny looping thing. We need that feedback. Any questions about that? We need it because if we just had a way to disable this, disabling the data would mean setting it to 0. How would I know if it's disabled or if the data line was 0? And either way, we're overwriting whatever's going in there. We need that looping thing. All right. This type of structure is called a D flip-flop with enable and can be used as a register. So this is like our basic unit of storing a bit. The two data lines are D, the actual data line, and Q, whatever was stored in there. The multiplexer in front selects via the enable. The enable signal is acting like the selector bit for which of the two signals to feed back into the register. The value of Q is relatched into D flip-flop. Yeah. Okay, when enable is low, the multiplexer selects the Q line. The value of D is ignored. The value of Q, whatever it is, will be relatched into the D flip-flop on a clock pulse. The value stored in the register is effectively unchanged. You overwrite it with itself. When enable is high, the multiplexer selects the D line. The value of Q is ignored. The value of D, whatever it is latched into the D flip-flop. Make sense? Happy? Sad? Cool. Okay. One may wonder why you go through the trouble of using, okay, well, in this case, the enable is low, no clock pulse with D flip-flop. High. Oh yeah, we could also maybe yeah, the other solution then would be, we kind of talked about this before. The other solution, you could say, okay, well, instead of having the enable activate or deactivate the data line, why not have it activate or deactivate the clock signal? If it latches every time there's a clock pulse, why not have it deactivate the clock pulse? Well, we've already talked about this. In general, you could do this, but but really leave the clock signal alone. Do not mess with it. As soon as you add an AND gate, you add some amount of delay, and you want everything to be synchronized as much as possible. Never screw with this clock signal. Leave it pure. Okay, and this is what I'm saying here. In practice, it can work. It could delay the clock signal, which can cause problems. Usually, it's a good idea to leave the clock signal alone. So, well, what if you want to store more than one bit? Well, that's easy. Just string these together, right? So here's 8 bits, right? What am I doing? Well, I've got one clock signal coming in that's connected to each of these registers. First of all, appreciate the fact that this is no internet apparently. Ugh. Let's see if we can fix that. Action needed. Oh no, it's going to make me sign in or some nonsense, right? Well, we'll find out. Appreciate the fact that this is clearly just a copy and paste of this general design, right? Nothing here is weird. Just note the clock signal is connected. It's the same clock signal connected to each one. The enable signal is connected to all of the multiplexers. They are all tied to the exact same enable signal. It's only the respective data lines that are different. Cool, right? So now I could go along and set all these data bits to make 1 byte, and then enable and clock pulse, and it'll latch all of that information at once. What's nice about these designs is they scale really nicely. You just copy, paste, 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 paste. A register symbol. So whenever you want to go and you want to implement a register, something like this, you could go and implement something like this all you want, but in general, we're going to create another layer of abstraction and create a register symbol. A register symbol really means this, which of course we know that this really means that D flip-flop, right? Which was, well, on the previous topic, but I don't want to hit next because we're going to mess up. So, yeah. So this is another layer of abstraction. This can mean a whole register. You'll notice that it's got the enable signal, it's got a clock, it's got the data, and a queue. We don't actually have a queue not anymore because usually when it's being used as a register, we just don't really care. You could, if you really wanted it, okay, if you can figure it out, you can just invert the output to have queue not. but in general, we don't really care. Now, what's nice about the register is you can go in and say, you're going to actually store 8 bits of information. So we can have one register store not just 1 bit, 8 bits, or more if we really wanted. You could scale this to, I imagine there's some limit inside of digital. I'm not sure what it is. But I can actually have this store, instead of 1 bit, 8, which is nice. Now to do that though, let's go here. Let's just really quickly, memory, probably under register. Hey, there we go. Wow. In order to, if you're like, well, how do I have input here? Like, how would I do this? If this, because this is a 1-bit input, right? How do I do that? Well, you can do it with something like there's a couple of options. You could do it with a splitter merger where we can have 8 of these merge into one 8-signal line. Oh man, this is tough with a, let's see if I can get it going. Some of you were getting really good with the trackpads, but not me. And then we would want this to be, how many input signals? 1, 1, 1, 1, 1, 1, 1, 1. And you can do, and then because the spacing is weird, you have a couple of options here. You can increase the spacing on here, spreading. You can make it 2 to make it fit nicely if you really want. Or here, what I like to do is go down and make it the small shape. Also, I think I showed you this before, but I'll show it to you again. If I call this like D0, check this out. If I go here and I paste, it'll automatically add numbers, which is kind of nice. It'll automatically increment. There's a setting in digital, I think if you go up into like edit settings, where you can toggle this on and off, like where automatically increment labels. But it's a pretty nice little feature there, so you don't have to go in and change all the labels. Comes in handy. Yeah. So there we go. How come that one figured it out? Anyways, you get the idea. So here's how I can do 8 inputs. Similarly, I can do 8 to 1, 1, 1, 1, 1, 1, 1, 1, right? And then that's how I could do the outputs. Another thing you could actually do is you can actually go here. Check this out. Whoop. Here, let's just get rid of this. Do a new one. I'm going to show you because I think it's cool and it's worth knowing. So if I go here and say this is 8 data bits, you can actually go here and change this to be 8. All right? Now, that then makes you wonder, well, how on earth do I oh, 8 bits. I need to change this to be 8 bits as well. Now, when I do this, you're going to be like, well, how do I, as soon as you go to do, like toggle this, you don't get to toggle it anymore because it's 8 bits. You click it and it's like, well, what do you want what do you want it to be? And I can go like, I think I can, yeah. Right? Okay. And then it's not enabled, so no data gets stored. I now enable it. Clock pulse, huzzah, 55, right? Now, also notice like 55. Remember, here's just a reminder of how nice going from binary to hex. First of all, OX, that means this is a hex number, okay? If it was 0B, that means binary, as like a tag, usually to be like, okay, this is a binary number. Usually when we're writing math syntax, if I say 11 base 2, like that, that means it's a binary number. In a computer with like ASCII characters, we usually do 0B, 1, 1. That would mean the binary number 1, 1. OX means hex. Remember, the magic of converting between powers of 2 or powers of the base to another one is, what is this binary number? 4 plus 1, 5. 5. Groups of 4 bits correspond to 1 hex digit. If I had a 1111, that's 15 in binary, that would be F in hex, which is pretty cool. That's a nice, quick and dirty. That's why we love hex. Is it's an easy way to briefly describe a binary number where it's easy for us to convert in our head. It's easier to convert, I think, quickly hex to binary than decimal to binary. And it's easy to go from like decimal to hex, I mean, kind of, if it's a small enough number. So it's like a way to convert a little easier, right? We can represent 8 bits here with two hex digits, which is nice. By the way, pretty neat. Anyways, so there you go. This is a nice, easy way to have multiple signals coming on a signal line, a single line. Cool. So there's the idea of RAM. Now, going back to thinking of these as 1-bit registers. I know I just showed you how we can make them go to like 8-bit registers, but let's go back to thinking these are 1-bit registers. If we revisit this idea that we had here, okay, where, okay, how are we controlling this? Well, remember, this is RAM, right? Each of these is a 1-bit magical thing that can store 1 bit of information. We know what these are now, but this is going back before we knew what these were. What do we got going on? Well, this row corresponds to 4 bits, so it's a nibble. 4 bits, that's like 1 4-bit word. This is another 4-bit word, another 4-bit, another 4-bit. This can store 16 bits, but really it's 4 groups of 4 bits. So if I want to select the first row, well, my address line, this is a decoder, right? I put in the number, like the address line will be 0000. Well, that would go and activate this one, and it could activate this row. Every other row signal will be 0, right? Because remember, with the decoder, only one of the output signals will ever be high. Which one? The one we select. Here to be the address line. Similarly for the output, right? Which one's outputting? Well, notice that based on this design, all of the registers are outputting always. Okay, they're always outputting their value. So whatever is stored in this bit column, let's say this is the least significant bit, so 0, 1, 2, 3. Whatever's stored in like bit 3 in row 0 is here, 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 here. I don't know what these are. I don't care what they are. But there is some value here. Each row's bit 3 is always being put to this multiplexer. Bit 2, bit 1, bit 0. But which one do I actually want to output? Well, the one I select on the address line. Cool? Cool. Is that clear? Do you have any questions, thoughts, concerns, comments, anything? Okay, 4x4 block of RAM. There are 4-bit memory addresses. A decoder is used to select which memory address is active. Notice how the decoded line activates all bits within a memory address. Multiplexers are used to relay the stored data out of the selected memory address. Notice that there is a multiplex for each of the 4 bits, yeah. So now we know that D flip-flops would work. Here's how we can modify this design with something that we actually know exists, right? So each of these is a register, a 1-bit register. I could achieve this same, I could simplify this design by having this be a 4-bit register to correspond to the whole row. But for the sake of learning about RAM, we have a 4x4 array of registers. What's going on here? Well, we've got our clock. And our clock signal, let's look at what's going on. The clock signal is going into each of these. All of these are connected to the exact same clock. That clock signal is unadulterated everywhere. When I originally designed this, I used the enable to deactivate the clock. And then I felt really bad about myself, so I fixed it, because that's bad, right? We don't do that. So here's the idea. Also, we have the data lines coming in. right? Notice the data line feeds into every register of this row. But which row do I actually want to store that data into? Well, that comes from this decoder from the address lines. Which one is being activated? Notice that this line is being ANDed with an enable signal. This is a write enable. We want to write to RAM. I know this can kind of sound, okay, wait, writing? Aren't we reading? Well, it's all relative, right? If I'm putting memory data into RAM, I'm writing to RAM. I know it might feel like, hold on, no, we're reading from somewhere into RAM. Yeah, it's all relative, right? So this is RAM. I want to write to RAM. I want to put data into RAM. I turn on write enable. It activates this AND gate, meaning whatever value is on here gets relayed. Remember, AND gates are great like that. If this is a 1, whatever value this is gets relayed. Is it a 1? Well, it'll be a 1. If it's a 0, it's a 0. Remember, that's the annihilator, right, of AND. True and whatever is whatever. Anyways, only one of these will be high, though. So only one of these signals will be high, assuming write enable is high. So which of these is actually being enabled? And the enable, all bits in the same row will be enabled at the same time. All registers, pardon me, in the same row will always be enabled at the same time. So that's putting data into. Cool? Now, how are we doing the output? Well, the same idea. We have the address lines going in to these multiplexers. Remember, every single bit in this column is always outputting to this output bit. It's always, whatever's in here is always here. Here is always here, here is always here, here is always here. But only one of them will ever be sent out. All right? Which one? The one that is specified on the address line. But I don't always want to be outputting from RAM. I don't want to be reading from RAM. I want to have control. When am I actually going to read from RAM? When I want to get data out of RAM. Right? One of these, because it's a multiplexer, one of these is always going to be relayed out. Whether it's a 0 or a 1, I don't know. Some data is always going to be output on this line here, and this line here, on this line here, on this line here. Meaning, no matter what, one of these rows of data is always being output. But I don't want that to be the case. I need to be able to control whether or not I'm actually outputting stuff. So what I have here is a brand new concept. It's not really a new concept. We kind of talked about it before, but it's a new idea. We have this thing here. Sometimes they're called drivers, sometimes they're called buffers, sometimes they have different names. But it's basically, I can turn on or off whatever's on here. Okay? When the enable signal is low, whatever value is here is not output to here. Whatever value is here is not output to here. Whatever value is here is not output to here and here. So this basically is turn on the signals or off the signals. But we've got a problem. What is, look, the data here is either a 0 or a 1, right? So let's take a moment and think about what's going on. We've got this fancy thing here. It's controlled. The data here is x. X is either a 0 or a 1, right? If this is off, what should be output of here? 0? But that's valid data. Remember that really, that means connecting to ground. So what is not, like, don't output whatever this is, but what if this is a 0? We're going to output a 0? It's a weird new idea that will become clear very, very, very shortly. But the trick is we add a secret, special third state. It's not a 0. It's not a 1. It's neither. Does anyone happen to know what this magical third state is called? We did talk about it before, but I know some students that took digital. What do you call it? High impedance. Sometimes also called a Z state. High impedance, meaning it's not a 0, it's not a 1. It's nothing. And do you remember going back when we looked at that AND gate, I made a point to be like, hey, look at that signal line between the two transistors. It's not dark green, it's not bright green, it's gray. That means there's no signal. It's a high impedance state. Basically, there's a lot of resistivity in there. There's nothing, it's not a 0, it's not a 1. It's not connected to 0, it's not connected to 1. There's nothing there. Okay? No signal can travel from here to here, whether it's a 0, whether it's a 1. Meaning, if I turn this on and this is a 0, that means this was connected to ground, meaning this signal is ultimately connected to ground. If this was a 1, that means this signal was connected to some high voltage source, some voltage source. Okay? But if this is off, I want it to be connected to neither ground or a voltage source. I want it to be connected to nothing. That's the idea. And this is where this concept of tri-state logic comes in. If we go here, let's open that. Discard. 4x4 RAM? Cool, perfect. Let's run this. So, see, look. See, they're all gray. How come I can't scroll? There. They're gray. They're not dark green. They're not bright green. They're gray. You'll notice that all of the input signal lines are dark green, but we're not outputting dark green. We're outputting gray. If we go here, let's enable read, meaning, again, read means output, like we're reading from RAM. And now, oh, they're dark green. This is enabled. We output whatever was in here. It's neat. In fact, you'll even notice, whoop, no. What is going on?
You can
There we
drag
go.
if you're like in
Here we go.
wave.
If you go here, you can even turn these into is 3-state input, where you can have an input be 0, 1, high impedance, which is neat. It's important, very important. Otherwise, our circuits won't work if we can't have this high impedance state. So it's kind of neat. When we start talking about the bus a little bit more, this will become a little bit more obvious, I believe. We've talked about this general idea a few times. I've hinted at it and sprinkled it throughout, but we're working towards a more concrete explanation of what's going on. Still no internet, huh? Let's try Eduroam. What do you think? Is anyone else having an issue connecting, or is it just me?
I had to trust the certificate again this morning, but other than that,
I don't trust anything.
really very happy.
All right, so there we go. So this is the idea. Before we had the idea, what would RAM look like? If we had this magic way of storing data, what could it look like? Well, now we have this magic way of storing data with that register. All right, so the above figure is a modified version of the same idea here. 1-bit registers are used to store the data. Clock signal is included. Control inputs for the memory address are added. Control inputs for the input data along with outputs are included. The design also includes control over what data is written to RAM and read from RAM. Cool. Controlling writes. Now, this is basically what I just said. When using a decoder to select a memory address, one of the decoded signals is always going to be high. This creates a problem as one of the memory addresses, sorry, I lied. This is talking about writing data to RAM. This is talking about the fact that we need these AND gates, okay? This creates a problem as one of the memory addresses would be written to at every clock cycle, even if not intended. Thus, there needs to be a way to have more control over when data is written to memory. One possible way is to have a write-enable signal toggle the clock. Again, don't do this. This can work, but you'd be evil. An alternative is to have a write-enable signal control if the decoded signals are not active, or active or not. This can be achieved by ANDing an enable signal with each decoded signal. Below is the figure showing that general idea. So here's that idea, right? I have 0, 0 selected. That means this signal is high, but write enable is not actually high, meaning that 1 and 0 is 0. Now, I actually, maybe a week or so ago, I was looking at this design and I realized I was unhappy with it because I could have simplified this, I think. maybe simplify isn't the right idea. And maybe this design really is a good design for us at this stage. But can anybody look at what we're doing here and think what we already know? It's not really a trick question, but based on what we already know, how could you redesign this to eliminate the AND gates? The idea is when this is 0, I want whatever the selected signal to be is 0. When this is 1, I want whatever the selected signal to be a 1. What could I change? Any ideas? A multiplexer? Very close. Remember, a multiplexer takes multiple signals and maps it to 1. I really want a demultiplexer. What I could do is, remember, a demultiplexer is a decoder, except it relays whatever the input signal here is to the selected output signal line. So imagine I put the right enable here and it fed into this. If it was 0 and we selected 0, 0 would be output. If it was 1 and we selected 0, 1 would be the output, thereby eliminating the need for the AND gates. But then we would need a demultiplexer. What's better? I don't know. Here I need one AND gate for each signal line, but I would only need one demultiplexer. I don't know. It's a design decision. What's better? I don't know. Both would work just fine. We're getting the same functionality. And isn't it, by the way, I feel like it's important to emphasize right now how, when you're writing code to solve a problem, you have design decisions to make. It's the exact same thing here. We have design decisions to make, but we're programming in a very different way. We're programming with these gates and these designs like multiplexers, decoders, and AND gates and registers. We're programming like physically with components, which I think is pretty cool, but it's the same idea. All right, so controlling reads. Similar to the decoder, multiplexers will always be outputting the selected signal. However, it is desirable to have control when we're actually going to output or read from RAM. Here, a problem arises. Typically, several computer components share a collection of signal lines to transfer data around. This is that idea of a bus. The bus is discussed later in a subsequent topic. Therefore, it's important that only specific components are reading and writing to the bus at a single time. Otherwise, the signals on the bus could become corrupted and lose meaning, right? Like if this was outputting, oh, there's a 0. The data bus has some important value on it, a 1. And I output a 0. I'm now trying to output a 0 and a 1 to the same signal line. We got a problem, right? No good. That's why we want that high impedance thing. I've got a 1 here and I'm outputting nothing. Nothing is being attached to that signal. When a component, instead, the component connected the signal to the ground, thereby, remember, when we output a 0, we're actually connecting something to ground, meaning if there was a 1 there, it gets sunk to ground, and we've created a short circuit. We got a problem. In other words, we need a way to output a 0, a 1, and nothing. This is where this idea of a driver or a buffer, it's got a number of different words. What do they call it in here? Components, wires? A driver. Okay, cool. A driver. A driver is a component that it can act as a switch. But instead of an on-off, it's on, or it's whatever the signal is, or nothing. So yeah, when it's on, it relays whatever the signal is to the output. When it's off or not active, it's the high impedance state or high Z state. This effectively means it outputs nothing. So this facilitates tri-state logic, 0, 1, and Z. We use the letter Z to mean Nothing. That's Z state. Therefore, drivers are ideal tool for controlling when RAM is being read from, like this, right? So here we have a 1, 0, 1, 0, but the drivers are not activated, meaning we're not outputting what RAM's like trying to output. Cool? I think that's pretty cool. RAM symbol. So we just learned about the register symbol. Well, now we've got RAM signal or symbols, right? Another layer of abstraction. We just went from like AND gates to SR latches to D latches to D flip-flops to registers, and now we're at RAM. We just blitzed through storing data by adding layers of abstraction, which is good. We like this. Digital provides several variations of RAM, most of which are not going to be used in this course. If we go into here, components, memory, there's a lot going on here. We've got register, ROM, dual port, counter with presets, counter, a random number generator, EEPROM, don't worry about those. RAM, separate ports, block RAM, bidirectional RAM, there's a lot. Register file, and there's a pretty cool one in here too. Oh, come on. Graphic RAM. Ooh, there's a way to do graphics, which some of you I saw were playing around with in the first lab when it was go look at the existing ones, right? And it would just make all those colors. Anyways, what's cool about that is you could treat RAM as this like array of data, and it outputs the values in that array of data to like some like visual representation, which is pretty neat. Doing so kind of hides a little bit of like, well, okay, what would the circuitry be to go from what's stored in RAM to what's being displayed? And there is some circuitry that we would typically have to design, but that kind of like hides it from us, which is nice because it gets quite complicated. Now we're talking about like video RAM, VRAM, which like your GPUs have, right? And that's how you store the data and what's being stored and displayed anyways. Cool. But the two big ones, why do I have uppercase and lowercase? Oh, that's so annoying. All right, digital provides several variations of RAM, most of which will not likely be used in this course. But two that will likely be used will be RAM with separate data ports and RAM with shared data ports. Okay? These are the two designs. Now, you might be like, when do I, like, okay, so they're different. Not really. One just kind of like, you'll see what I mean, right? I don't show you. So one, we have data in and data out. That would be more along the lines of like what we saw right here. Like this, right? Data in, data out. But if you consider the fact that this is typically what we would have. We would have some bus, okay? And here we have RAM. Right? Data in, data out, right? Now, if you've been paying attention, you might go like, what do I care? I mean, this is the same signal line as it's all the same signal line. Like they're separated, but they're not. If data out outputted some value X, that means X goes everywhere, right? And X would be back on the data in, right? Now remember, we're controlling when we're reading and when we're writing. But when I'm reading from RAM and outputting the value X, X is going to be on this signal line. Right? Is that clear? What I mean is when I'm reading, read whatever value is here. When I'm writing, write to whatever write whatever I well. If I'm reading from RAM, output to here. If I'm writing to RAM, input from here. It doesn't really matter. It's the same signal line, right? Because I could draw it. If it was like this, I could also just say like, well, right? Like it doesn't really matter where I connect the output to, as long as it's the same line, right? So the only value you really have is, sometimes it's nice to have that visual clarity, inputs, outputs, but at the end of the day, it doesn't matter. It's the same thing. Somebody had their hand up. So here we go. RAM with separate data ports and RAM with shared data ports. RAM with separate data ports has independent input and output lines, even though they're not really independent. Data can only be written to RAM through the D in. Data can be read from RAM through D out. RAM with shared data ports, shared input and output lines, data is written to and read from RAM through the single data line. The RAM design discussed above aligns more with the separate data ports, but we can modify this by just, think to this, right? We can have these lines go back to here, right? And it really wouldn't matter. So the style of RAM we've discussed here is real RAM. This is RAM. I'm not giving you some cheesy design. This is RAM. But this is a special type of RAM called static RAM. It's very high quality. This is the RAM you want. But it's expensive. It's very expensive. Whenever data is latched into RAM, it will remain there until power is removed from the circuit. No questions asked. That's it. But in modern computer RAM, we often find DRAM, dynamic RAM. You could get static RAM for your computers and it'll work just fine. It's the same thing. And static RAM is objectively better until you consider cost. We use static or dynamic RAM. The details are nuanced. We're not going to get into it, but instead of using a form of latching the data, we use a transistor and a capacitor. So the capacitors are little electronic components. You'll see them drawn like this, two parallel lines. Depending on the type of capacitor, there could be variations, right? It doesn't really matter. It's important that the lines are the same, otherwise you can have like a power cell. That's usually what that means, but anyways. Capacitors. And what's nice about a capacitor is when you apply a charge, it holds a charge very briefly. So if you apply a charge to a capacitor, the capacitor charges up and it holds that charge. And if you turn power off to the system, the charge will dissipate, but it takes a second, right? A very brief second. But it doesn't, when you turn off the circuit, there will still be a charge because of the capacitors. You know how when you turn it off and on again, right? You know how when you turn it off and on again, how you turn it off, but you gotta wait a second. You can't just go on, off, on. Well, it's because there's a lot of capacitors and charges stored in your computer that when you turn it off, power's still there for a brief moment. That's why you always wait a second, make sure everything dissipates, turn it back on. There you go, right? Capacitors. They're also a great way to be like a low pass filter, but let's not worry about that too much. Anyways, they store a charge very briefly. So we can use these capacitors to store bits of information, but the problem is they only store the information very briefly. So there needs to be some circuitry and logic where we have this system that goes through and recharges all the capacitors really fast. And it's constantly scanning RAM. Anyways, but so this RAM, this is the static RAM. This is real deal, right? This is awesome. But in practice, we use a cheaper and just fine RAM called dynamic RAM in practice. But static RAM is nice stuff. Cool. Do we have any questions about RAM? All right. Well, because we don't have internet, let's do an activity really quick. Draw me a 1-bit register using a D. You can use the abstract idea of a D latch in your 1-bit register. And you have to have it handed in to me by before 10:20. By the way, last time, people didn't get perfect because you didn't label things. If you don't label things, I don't know what's an S, I don't know what's an R. Here, I won't know what enable, C, D, Q. I'm not guessing. I can't make a guess for you. So make sure, and straight lines. No, not straight lines. Don't forget your name, student number, and don't hand in anything for anybody else. I mean, draw me a 1-bit register. I don't care where this design comes from. Just draw me a 1-bit register. By the way, I'm only going to say this to everybody because I always see this happen. I just see people are sitting there and then they turn their head to look at that screen. But remember, no matter where you're sitting in this class, if you look straight ahead, there will be another screen. So you don't need to crank your neck, right?
Yeah.
I guess I'll stop recording now too. No need for this.